Mixture of expert models act like giant companies where most specialists sit idle. Since only a handful work per task, this massive redundancy creates 97% inefficiency and a major compression challenge. A mixture of experts model processes information by routing inputs to specialized subnetworks. This router assigns a gate value to each expert, which acts as a weight. By calculating this weighted sum, the model adapts its architecture to every unique token, from cat to dog. We can compress these models using two different philosophies. Pruning simply removes less useful experts and renormalizes the remaining choices to maintain the total probability. Merging instead attempts to preserve knowledge by blending specialists into a single entity. However, while merging keeps more parameters, it forces previously distinct experts to share one gate, sacrificing the dynamic independence that allows the router to fine-tune its selections. Benchmarks suggest merging is superior for knowledge preservation, but these scores are limited. Does this still hold up for generative tasks like coding? Merging creates a fatal flaw by destroying the router's ability to dynamically balance skills. While separate specialists allow for precise task-specific weights, a merged expert locks that ratio into a fixed mixture. This loss of flexibility increases the error bound because the model can no longer adapt to input variance. To minimize error, we must identify experts with the least contribution. The REAP score measures this by multiplying an expert's average gate value by its activation magnitude. Even a highly active expert is pruned if the router rarely grants it high weight, preserving only the most impactful knowledge. Benchmarks reveal a surprising reversal. While merging holds its own in multiple choice tests, it collapses in code generation. This suggests that complex tasks require a coherence that merging's fixed blending destroys. REAP succeeds where other methods struggle. While rivals collapse at 50% compression, REAP's performance stays nearly lossless by uniquely identifying a model's most essential layers. REAP scales flawlessly to trillion parameter models. Results from Quen and Kimi prove we can have these architectures while maintaining near lossless performance on complex generative benchmarks. Pruning wins because it preserves the router's independent control over experts. These separate gates enable the coordination needed for complex generation, making REAP the optimal compression criterion. We can now compress massive trillion parameter models by half while maintaining nearly identical performance. This efficiency makes elite-level intelligence consumer hardware friendly, proving that smart pruning like REAP preserves the dynamic control that merging often destroys.